Hi everybody, today we're going to look at a couple of properties of a coil, and hopefully with understanding the basic properties of a coil we can understand some of the basic properties of a transformer. So when I take an AC source and apply it to a coil, we know that as soon as I have current flowing through that, I will have an electromagnetic field that builds around that coil, which will allow a electromagnetic action on the core itself. I will create electromagnets. So we can use a couple of the left-hand rules for coils to determine the north pole, determine the direction of that magnetic field. But in basic principle, we know that as current is entering this point, there's a magnetic field that is around that conductor. And so as that magnetic field, it starts to cross and cut across that conductor. So as soon as we have relative motion between a conductor and a magnetic field, I will have a counter EMF. And I like counter EMF because counter EMF is a voltage. That's what I find fascinating about a coil, is that I have a voltage of a source and then I will have a voltage that is produced. Important thing about that counter EMF is that the voltage that is produced is always opposing the change that created or what caused it. So if I have a current that's flowing in this direction, that counter EMF is going to produce a current in the opposite direction. What that causes is a lagging relationship between current and voltage, because it takes a period of time for that current to reach a maximum value as it flows through this coil. Well, as soon as I have that current that is entering and I continue to have current that's flowing through this, the magnetic field that builds around this coil, it is also expanding and contracting. So because of my AC source, that current and voltage are continuing to increase and decrease, the magnetic field that is here will continue to expand and contract. So when we look at the basic properties of a transformer, transformers that work on mutual induction, I have a solid core and then two coils that are electrically isolated from one another. So when I take an AC source and apply it to this coil here, as soon as I energize that source, I will have current flow through that coil. I will have a magnetic field that expands and start to cut across that conductor. As soon as I have relative motion between a conductor and a magnetic field, I'm going to have a counter EMF. Well, we really have to look at what this magnetic field is doing. So this magnetic field on the core is going through the entire core, and it continues and establishes those lines of magnetic flux throughout the core. And as we know, as we just seen, that magnetic field is continuing to expand and contract. So if we look at this core that's electrically isolated from my first winding, this winding, I now have the lines of magnetic flux that are flowing through the core, and they are continuing to expand and contract. So as soon as I have a magnetic field that is expanding and contracting and cutting across a conductor, I will have a voltage that is produced, a counter EMF. So on this secondary winding, based on that relative motion between the conductor and the magnetic field of this winding, I will have a voltage that is produced. That voltage that is produced is all dependent upon the number of turns that are present on that winding, and the volts per turn is actually established by this winding over here. So we will always give this winding a name. So the winding that is attached to the source will always be the primary winding. The voltage that we will utilize for the load. So say we actually change that out, that's our light bulb. This winding that is connected to the load will be our secondary winding. So the primary is connected to the source. The secondary is connected to the load. And it doesn't matter high voltage, low voltage, step up, step down. That is what we define as the primary and secondary voltage. Well, I hope this helped. We'll see you next time.